Okay, for this part, okay, I think I will explain for today if possible how to calculate the residual properties is um, I'm trying to we do until the I'm not sure whether can be generalized or on the cubic equation of state. So that's why you need the knowledge from chapter 3. Okay, because all those data that the data that you need uh, the data in table 3.1 as well as table B1 or C1 in appendix you have to use to calculate the residual properties. Okay, so what we're going to cover for this topic is introduction to the thermodynamic properties, fundamental properties relation for the homogeneous space. Okay, you have to remember homogeneous space. I think for derivation, I don't think I will explain clearly. Okay, just the application of the equation, how to use that equation to calculate the residual properties before you combine with the H. Generally, the thermodynamic properties that we will consider is gives energy, entropy, as well as entropy gives energy, enthalpy. Okay, so to get the actual thermodynamic properties, you need these residual properties plus with the thermodynamic properties at ideal gas conditions. I mean at the standard conditions. Okay, so once because for example delta H for the enthalpy equal to delta Hij plus V delta HR lah. Okay, so that is the actual enthalpy lah. Okay, and then yeah, this is what we're going to focus on, the residual properties. Okay, equation of state, how to calculate by using equation of state, virial as well as cubic equation of state, and then generalized correlations, virial as well as Lee Kessler. Okay. I think so for generalized, definitely you have to use uh, a data in appendix so that you can do the interpolation. Okay. Slide yang saya download sama dengan yang lepas, maksudnya
We download the slide that state the chapter 6, but the file name is actually the chapter 4.
oh chapter 4. Okay, okay. Aduh. Alah lah pula. Sekejap saya kasih. Wait I pause first. After we deal with the residual properties, how to determine the residual properties by using equation of state, generalized correlation, and also from the uh, table and diagrams. But mostly we use the equations, okay, whether generalized correlation or equation of state, because table and diagram is, we have a very limited of table and also diagram this data. That's why we need this all this equation for the calculation of the residual properties. Similarly like a chapter 3, right? No, not it's a very limited of data for the calculation of the thermodynamic properties. Okay, and then so we will deal with the heterogeneous phase, two-phase system, meaning that vapor and liquid. But this one we will more focus on the in chapter 11 and chapter 12, because for two-phase system you need a coefficient, we call it as a activity coefficient, and as well as uh, fugacity coefficients. Okay, fugacity for the gas, and then for the liquid we deal with the um, activity coefficient. So you have to remember, because at different pressure is going to be different. Fugacity coefficient or also different uh, activity coefficient. Okay. And then thermodynamic properties from the thermodynamic tables and diagram. And this one is similar. Okay, but mostly we are focusing on the homogeneous. Okay, later chapter 11, 12, and then chapter 10 and chapter 13, we deal with the reactions. Okay, reaction as well as the equilibriums. Okay, because once for the binary systems, we cannot separate if the system is not in equilibrium. Okay. Okay. So let's see the introductions, fundamental property selection for the homogeneous phase. This is fundamental before we get the equation for the residual properties, as well as we will see the what is the residual properties lah. Why we call it as the residuals? Okay, because if you remember for delta H is equal to integration of CPdt, right? But that one is applicable for the ideal gas, right? But if we deal with the non-ideals, so that CPdt, we will expand that equations, just like in chapter 4. Okay, and then that is if only we deal with the certain pressure or temperature. Okay, if you still remember like a Taylor series, right? The longer the equation is going to be more accurate. That's why we have another properties or another equation that we have to add for the for example, just now it's enthalpy, right? Equation for the enthalpy at the end of the equations to get the correction for that for your equations, so that you can get more accurate value or data. Okay. So if we consider the process design analysis in for the system and then out, okay. So to find the volumes, yeah, we completely prepare, okay, whether is it ideal or ideal gas or liquid. So how about the other thermodynamic properties such as enthalpy, entropy, internal energy? So we have no idea what is the pressure and the volume function, right? So before that, I want to know that what do you understand about the entropy, as well as yes, what do you understand about the entropy? Anyone? Ada siapa-siapa tak? Apa? Nurul Ain Azhar. Nurul Ain ada kat situ tak?
Okay, Doctor.
What do you understand about entropy? Ada? Faham tak? Anyone? And what do you understand about the Gibbs energy? Saya bukan, I don't say that I want the definition, only what you understand.
What? From my understanding, it is heat, thermal energy, Doctor.
Memanglah, of course, all is energy. Yeah, now what do you understand about the entropy? Last time when you learn at the energy balance, right? What's the definition of the entropy? Ada belajar tak? Did you learn?
Ada, Doctor.
Ada. What is the definition of entropy? Hmm. Tak tahu. Anyone? Measure, memang. Yeah, of course there's measure of disorder. What do you understand measure of disorder? Siapa tadi? What do you understand disorder? Any example? Akmal Arif. What do you understand about the measure of the disorder? Anything? Anyone? Who else? Mana tadi? Siapa nama tadi? Mode of waste energy. Randomness of particle, yes. Akmal Arif. what do you understand of the randomness of the particle? What is the equation for delta for the entropy? Akmal Arif, Akmal Arif Islam. Can you unmute?
Sedap.
Ah,
Tak ingat equation dia Doktor.
but what do you say about the what is it?
Randomness.
What do you understand about the degree of randomness?
Um, I understand.
Anyone?
I'm not sure how to explain Doktor.
Okay. So, of course, yeah, that is correct. There is a measure of the degree of randomness. It is, for example, like ice to liquid and liquid to gas, right? Okay. Which one is more random? Gas, right? Okay. If compare with the liquid, gas is more random. And if we compare liquid with the ice, liquid is more random lah. So meaning that if your entropy is positive, so the how to say for conversion of gas to the liquid is much easier. Compare if you want to uh, make it a liquid to the ice cube lah, because it's a naturally will melting, right? Rather than you put the energy for the liquid to make it the ice cube. Similarly also for the liquid to the gas lah. Okay. So you just boil it, right? Just naturally, it's gonna be more easier rather than from the gas to the liquid. So that's why we call it as a measure of the degree of randomness. Secara it is secara natural lah. Because if on opposite you need an external energy lah. That's why your system must have positive entropy. Okay, so you can get a less energy lah. Okay, so that's why is S equal to delta Q divided by T. Okay, and it's related with the Gibbs energy lah. For the Gibbs energy, we want to see the degree of spontaneous. What do you mean by spontaneous? Okay, anyone? Whether your reaction is spontaneous or not? Okay, so macam ni lah. We actually is the targets we measure to see the equilibriums or whether your reaction is spontaneous or not. Okay, for example, like do you know the reaction about the biodiesel productions? We need the 1 mole of the FFA plus with the 3 mole of methanol. Okay, but this is a reversible reactions. Okay, in order to push it forward, kejap ada calling masuk Okay, sorry. Where we stop? Okay. For example, like by this day, right? So unit actually is based on theory is 1 plus 3, 1:3. So to make it a shift or forward, okay. To make it a spontaneous, okay. So we need more excess methanol so that the direction can push forward, okay. If not spontaneous, meaning that your Gibbs energy is positive. Okay, Gibbs energy spontaneous is negative and will proceed until it reach the equilibrium. When it reach equilibrium, delta G equal to 0. Okay, so if you still remember about the uh, equations, okay, delta G equal to delta H minus Ts. Okay, Ts. Okay, generally this one is going to be negative. Okay, so you need this one as a positive so that your Gibbs energy must be to get energy to get the Gibbs energy is negative so that your reaction is spontaneous lah. Okay, that's why your entropy must be positive. If not, you need the external energy to assist your reactions. Okay, more energy. Okay, but it's depending on the to get this Gibbs energy is depending on entropy and also enthalpy lah. Okay, okay. Okay, that is a introduction about Gibbs energy and also entropy. Also, please remember that equations. Okay, we want to determine whether your reaction is spontaneous or not. Okay, spontaneous negative. Okay, until it reach equilibrium, Gibbs energy equal to 0. So once the Gibbs energy is equilibrium, there's not going to be shift to the left or to the right of the reactions. Okay. Okay. Faham eh? Okay, so for thermodynamics, if you look at here that we need to develop such relations, just like now delta G equal to delta H minus T delta Ts, right? Okay, that is the relation. We call it actually is the fundamental properties of relations. Okay, and then since you want to calculate this enthalpy, entropy, right? Okay, so previously on the previous chapter, you just focus on the PVT, right? Okay, but now you are focusing on the second law of thermodynamics, which is involving the entropy. Okay, you have to remember that that is the second law of thermodynamics. If a heat capacity is a first, okay. So how to calculate this one? Of course, you need the by using general correlations and also the relationship, or we call it as a properties thermodynamic properties relations. Okay, so for the first law, okay, I think all of you already know energy cannot be created or destroyed. You have to remember that. Okay, and this one is entropy, delta S equal to delta Q divided by T. Okay, so if you look at there, isolated system not in equilibrium will tend to increase over time, approaching a maximum value at equilibrium. So this is related with the Gibbs energy. Okay. So let's see the properties relation for the homogeneous phase. You have to remember that homogeneous phase, whether liquid or gas. Okay, for the other thermodynamic properties, such as P, V, T, U, and S, this is we call it as a primary lah. Okay, but there is another thermodynamic properties which is derived from the primary. We call it as a secondary or other thermodynamic properties. One is the enthalpy, Helmholtz energy, and also Gibbs energy. But we are only focusing on this one. PV. Helmholtz ni, this one is for the closed system and generally under molecular levels. We will focus on the Helmholtz and closed system. Okay, that's why it's involve internal energy. Okay, but we want to cover. If you learn about the quantum, yes, you will use this Helmholtz energy. Okay, so if we consider the closed system homogeneous single phase, no change in the composition, we are still not considering the composition. Okay, so if you deal with the vapor and liquid, which is a two phase, yes, composition is the primary parameters that you have to consider later when you deal with the binary system. Okay, in chapter 10, you have to calculate the composition. Okay. Initial condition P1, P1, and also final condition P2 and T2. Okay, first law, of course, if you still remember, U is equal to Q plus dW. This one, right? Similarly, also for the enthalpy. Okay, so if reversibles, this one is become T dNu and dNu. Okay, so just this is, I think, the normal equation, general equation. So similarly also for the enthalpy actually. Okay, all this equation actually we call it a thermodynamic properties relation. And this is just a derivation before we reach the residual properties equations. Okay, so this is what we call it a properties relation, thermodynamic properties relation. This is we call it a thermodynamic. Delta H, delta G, delta A, and also delta U. Okay, I'm not gonna explain the derivation. Okay, another form is we call it Maxwell equations. So this one in terms of a partial derivative. Okay, once you combine with this Maxwell and also properties relations, actually you can get if you combine, you can get another expressions in terms of for the DHCP, right? For this one. Okay, if you combine. So if you look at here, this is a general equation that you know, right? When you learn at the previous chapter and also mass energy balance, right? But how about this one? Right. There's another how to say questions. Yeah. So our concern is how to determine this one actually. This one is, I think, is no problem. Okay, you learn at the chapter 4, ICP. So just use that latent heat, right? Equation sensible latent heat. Okay, so you can solve it. Heat of reaction, heat of right. So the problem is here. Okay, you see, right? Okay, once you expand the equations, this one. This is the additional equation here. Okay, once you expand this one. But the problem is delta V, delta T. Well, how can we determine this one? Okay, it's something like there's an additional equation to the previous equations. Right, that's the problem. This one is for the DH. Similarly, also for the enthalpy, right? For an entropy, right? This one. Okay, so this is what we want to find and that's what we have to calculate, okay, from the previous chapter. Okay, for the entropy, CPDT is a difference between the enthalpy. Okay, so this one is you have to find from the chapter 5 lah. The integration also mean heat capacity, IDCPH, and also IDCPH. Oh, for the entropy, IDCPS and MDCPS. Okay, mean heat entropy and also integration for the entropy. Okay, so this is our concern. Okay, please remember that one. Okay. And this one is the expression after you for the internal energy lah. Okay, so from that, okay, as the summary, okay, this one lah, okay, the equations, but this one is still the beginning before we get the final equation lah. Okay, so this is the new form of your thermodynamic properties equations for the especially for the enthalpy. Okay, entropy I think is a new for you. Okay, for this course. Okay, once you rearrange for the ideal gas, of course, if you still remember the HIG CPDT, this one is only T2 minus T1. This is only applicable for ideal gas. Okay, and this one is DP. DP is a P2 minus P1. Right, so you can get delta SIG. Okay, this is for ideal gas. Please remember, and we denote as a IG here, ideal gas. Okay, how about the real gas? Okay, that's the problem. Okay. This one is for the liquid. Similarly, also for the incompressible liquid, actually is a very small compared with the gas. Okay, because it's not changed with the volume, right? Okay, for the liquid. So if you look at here, also they have some additional equations here. Okay, or parameter. Okay, for both equation. Okay. And for the internal energy, similarly, okay. So we can say that, or we can summarize. Actually, there's additional parameters that you have to determine compared with the previous equation. Okay. How to find? Okay, let's see. Okay, this is the remaining properties, SHG and also UHPV. So I don't think I'm going to explain this one. Okay, so if you look at here, from the previous equations, right? This one, right? PV and PV, right? Okay, first, how to determine these equations? How to determine this value? Okay, there's a one step. There's a some step to determine. Okay, first, there's a, we call it a graph method by using a graph, but this one is a quite tedious. It's a lot of many steps. See, and then you need various data to calculate the residual. We call it, I just call it a residual properties lah. Okay, at the end of this one. Okay, so and then another method is by using equation of state, and the third one is by using generalized. Okay, which one I would suggest is depending on the if you compare graph, cubic equation of state and also generalized, you have to choose cubic equation of state and also generalized. But if you compare between generalized and also cubic equation, it's depending on the what type of the gas. Okay. Similarly, like a previous, you using Penn Robinson, soft Reddick Kwong, right? Okay, of course, that one is more accurate rather than Reddick Kwong or Van der Waals. Okay, and depending on the omega lah. I already explained what is the function of the omega. And also you have to consider the pressure and also temperature. Okay, so whether it's low to moderate or moderate to high. Okay, and if just low to moderate, I would suggest it's just using a video. That's all. Okay, no need to go to a Lee Kessler or cubic equation. And yeah, you have to consider whether it's polar or non-polar. But generally, we deal here is non-polar. If not for the polar, you have to find an equation from another reference. Okay. Okay. So in order to use these equations, okay, because this I think is quite difficult to find dV over dt and dP, right? So we need the initial T and final temperature and pressure. We have to find to get the PV data and also CP. Okay. So first, calculate delta Hij using CPIG and then see the difference, because for the residual properties actually is H. This is actual enthalpy. I just use enthalpy Hij. This is plus HR. Okay. Okay. We want to find this residual. This is the relationship. Okay. And then the real enthalpy we just add this one. Okay. So how to determine? Let's see the definition of the residual enthalpy. Okay, the example. Okay, so if we consider the generic residual properties, okay, Mr is equal to M minus M, Mig. So M can be V, U, H, S, and also G. Okay, so please remember M is just what we call it as a symbol. It's just a symbol. Okay, it can be VU, but generally we deal with H, S, and also G. We more focus on this one. Okay, so to calculate these residual properties and to calculate the real thermodynamic properties, you need hypothetical part. Okay, please remember you need the hypothetical part. Without hypothetical part, you cannot solve the problem. Okay, for example, you have a hypothetical part here, right? Delta H, okay, and then from the initial to the finals, okay, Hij, right? This one Hij, of course, if you still remember. Yeah, this one. So once you rearrange, because Hij you calculate from the mean heat capacity, right? And you have this one. This is real. Okay. This is the real one. Okay, so H1 minus Hij lah, or Hij minus H1, because this side. So Hij minus H1, and this one is opposite. Okay, and this one is the same H2 Hij. So once you rearrange, you can get this one is equal to HR. Okay, this one is negative lah because it's the opposite, right? H2 minus Hij, real minus Hij, so you can get residual. So once you simplify, you can get this one. So this one you have residual properties. This side also you have a residual properties, but this one is negative lah. Okay, because delta Hij minus delta Hij minus H1. Okay, so this is based on the hypothetical part. Okay, so please remember on the left and right there is residual. If your hypothetical part is only like this, okay, so on the left side don't have, only on the right side. Similarly also for like this, meaning that this one H1 only have residual, on the right side don't have. Okay, so we need to figure out how to determine this delta HR, or if not your calculation is going to be only this one, right? Delta this one, so not accurate. Okay, so there is three method as I told you. Okay, first method is by using a graph. Okay, let's see the derivations. Okay, this is just derivation, no need lah. I just see explain the final equations. Okay, for the residual Gibbs energy, you need this equation. Okay, and then for the enthalpy, you need this equation, and this one is for the residuals. Meaning that you have to put here lah. You have to substitute this one. Yeah, this one. Okay, you have to substitute. Okay, our problem is how to determine this one. Delta P, right? Delta Z, delta T, delta dP. This one also. That's why I told you by using this one is by using graph method. Okay, I just call it as a graph lah, because you need the data. Okay. Okay, so based on the enthalpy of the real gas, okay, if you look at here, we already derived just like a previous CPIG T2 minus T1 plus H2R minus H1R lah. This one is residual. So that one is for the enthalpy, but for the entropy, okay, you have to refer to chapter 5, this one, the mean heat, not mean heat, mean entropy lah. Okay, so please look at here, chapter 5, I don't know which page, MCPS lah. If all book, equation 5.17 and 5.15. Okay, I think for the new books is similar. Equation 5.5, 5.17. This is only for entropy. Okay, if you want to learn more about the entropy, you can read this chapter 5. But we never focus for this course. Okay, so and they have this one additional T2 minus T1 and P2 T2 divided by T1 and P2 divided by P1, and also residual here. We want to find this residual. This one you can just replace. Just similarly like a mean heat capacity and also integration of the heat. Okay, heat capacity. Okay, so this is the equations. You have to highlight this one. Don't remember this equation. Okay, enthalpy and entropy. Okay, so since we already defined from the previous equation, this one, enthalpy and entropy, so we have another equation here. If you remember, this one is a mean heat capacity plus with delta Hij. Okay, this one is for the entropy, Sij, and we have an additional equation here. So how to determine this one? Okay, first is graph. What else? Equation of state. You have to remember, okay, this one you have to write down, and also generalized correlation. This one, equation of state. They have, we can divide. Generalized also can divide too. de Kessler and also virial. Question of state, of course virial and also cubic question of state lah. Okay. Okay. Okay, let's see the example if we want to determine by using a graph. Okay. Okay. Calculate the enthalpy and entropy of saturated isobutane. Wait, Okay. So if you look at here, calculate the enthalpy and entropy of saturated isobutane vapor at 360 Kelvin from the following information. Okay. Table 1. Okay. Give a compressibility factor data value of Z for the isobutane vapor. Okay. The vapor pressure of isobutane at 360 Kelvin. Okay. Is 15.41 bar. Okay. Set delta H naught Ig 18.15 115 kilojoule and delta Sig 295 0.97 joules. Okay. Ideal gas reference state and then 300 Kelvin and 1 bar. Okay. And ideal heat capacity, if you look at that, is given already. So what you have to do is given also the data. Okay. If you look at here, different temperature and also various temperature and also various temperature and also pressure. Okay. So this is a value of Z compressibility factor. Okay, at different temperature and pressure. Okay, you have to remember that. Okay, this one is 300 Kelvin, 360, 370, 380. Okay, so what you have to do, you have to construct a graph. Okay, so once you construct graph, compressibility factor versus temperature. Okay, for each pressure, this is the pressure. Okay, and this is temperature, and this one is compressibility factor. Okay, so just construct the graph. Okay, for starting from 0.1 until 15.41, and then you have to find the tangent line at 360. Okay, the tangent line. This is a middle, in the middle. Okay, if you look at here, this is we consider as the center. Okay, just find the tangent lines. Okay, this is per step, and then you have to calculate the area. Okay, that's why I told you it's quite tedious, because from the tangent line, so you can get the slope, right? Okay, so from that ones, because this one, if you calculate the tangent line, because the equations, right? The equations, you're right. This one. Delta Z, delta T, meaning that Z2 minus Z1, delta T, T2 minus T1. Okay. Okay. You get it? So, meaning that if you find the tangent line, this one is Z2 minus Z1 and also T2 minus T1. This one. That's why you have to find the tangent line just to get delta Z divided by delta T. Okay. And once you determine delta Z, delta T divided by P, so you have to calculate the area under this graph. This is for blue, for this one. And then for red one, this one. Okay. You have to calculate. Similarly also for the red one. Okay. You have to calculate just to get the area under the graph. Integration actually is integration, or this is you know, right, delta Z delta P is the area of under the graph. Okay, So once you determine, okay, you have to calculate the area of this graph. Okay, so you remember this one, how to calculate. I just make it a traditional method. Okay, divide, then divide. Okay, divide, and this one is a triangle, right? Similarly also you do for the blue one. Okay, this one is how I calculate lah in terms of rectangle and also triangle. So I get this one 24 1, and then I combine, I get this one. Okay, so finally you get the value of this one. It's almost this one is from the book, this one the one that I calculate. Okay, not really, it's almost similar. Okay, then you substitute into the equations, this one, delta HR 360, right, times the temperature, and also delta SR, and then substitute into here. Okay, this one also, so you can get the SR and HR. Okay, so once you determine HR and SR, you can substitute into these equations, this one, this one, and then you just calculate this one, and also SIG, HIG from the, this one HIG is from the table, right? If you remember from the appendix, so you can calculate this one, so you can calculate the real enthalpy and also real entropy. Okay, any questions about this method? You want to use this method for the calculations?
One.
Okay, so there's a many step if you want to use this graph. Okay, but generally I think if you have the data, enough data like this one, right, for each temperature and pressure, I think you can use this method but if just a single, what to say, information is just at that particular temperature, right, I don't think you can use that. Okay, so that is the method how to use the graph method. So but it's quite easy lah sebenarnya. Okay, is a direct, can get this one. Okay, so that is a graph method. Okay, let's see the second method, which is by using equation method, and the third one is by using nearest correlations. So you have to remember this one, these two. Okay, so let's see the equation of state. For the equation of state, okay, this is to replace the previous method. Okay, which is we can solve directly without the graph. Slide yang saya dah apa ni? Okay, so you can solve for this one actually, for the residual without the data provided, right? Okay, so and then it can reduce the calculation step. Okay, and I think some equation is more accurate, and you can consider the condition whether it's low to moderate and moderate to high. Okay, so it's divided into two by using a real equation of state and also cubic equation of state. Okay, this is for gas and also for vapor. Okay, we use this real equation and also cubic equation of state. Okay. Okay, so let's see for the two terms. For the two terms, is the expansion from the previous equation in chapter 3, right? Just substitute into this equation. If you look at here, that z minus 1, right? Because generally is z equal to 1 plus bp. Just substitute into this one so you can get gr lah. Okay, similarly also for hr and also sr. Okay, but the problem is the coefficient of b lah. Okay, if you cannot find for each for the target compounds or target pure component, so I think you don't have to use this question, because B you have to find from the information from the engineering handbooks or any chemical engineering handbooks. Okay, similarly also for the third term, Third term is just extensions. Okay, this is an alternative form in terms of a row. Okay, so if you use a row, a similar row, you can get from the chapter 3. Okay, and then three terms, just some extension with the row. Okay, this one is just videos, but for this one, I don't think I didn't say is I'm not gonna suggest it, but you have to see this value of P lah, P and B and also row. Okay, how to find this one? Okay, so you need the data for the second and third virial coefficients. Okay, it's like a B a row. You have to calculate residue. Okay, the one that I want to focus is more to on the cubic equation of state. Okay, how to determine? They have two cases. Okay, our first cases is sigma is not similar with the epsilon, and another one case 2 is sigma equal with the epsilon. Okay, so this is the equations for the cubic equation of state to determine residual properties. If you look at here, this is the only the problem that you have to determine. Okay, Q is you can determine from chapter 3. Okay, the problem beta also you can determine, but the problem is this one. How to determine this one? So you have to differentiate this d ln alpha tr divided by d ln tr. Okay. Okay. So if you look at here, there is two cases. Okay. If you refer to table 3.1, right? Table 3.1 in the previous, they have alpha is equal to sigma and alpha not equal to sigma. Okay, this one is only applicable for van der Waals. Okay, for the Peng Robinson, soft Reddy-Kwong, and also soft Reddy-Kwong and soft Reddy-Kwong and also Peng Robinson, we use this equation, the first one. Okay, this one. This one is only for van der Waals because epsilon equal to 0, sigma equal to 0. Similar, right? Similar. Okay. But for Reddy-Kwong, if you refer to table 3.1, the parameters, sigma is equal to 1 and epsilon is equal to 0. Okay, so it's not similar. So you have to use this one to calculate I. Only for calculate I, okay? So substitute into here. Okay, and then you have to solve it by using equation 3.52 and also 3.56 for the liquid phase. So meaning that 352 is the vapor liquid vapor apa panggil vapor roots, right? Vapor like roots equation and also liquid right roots of the generic cubic motion set. If you remember this one, Z, you have to determine Z first and then you have to substitute into PV equal to Z other thing. Okay, so this one. Faham? So if you still remember that there is a vapor and also liquid. Okay. So let's see example. This one we do together. So please take one paper and we do together and I want to know the answer. Okay. Find the value of residual enthalpy. Kenapa saya punya annotator? HR and the residual entropy SR. Saya guna macam ni lah. Sebab dia hilang je lah saya punya tu. Okay. So entropy HR and butane gas at 500 Kelvin and 50 bar. So it's a high. Temperature is 500. Right. Kelvin. Pressure 50 bar. Find TC. PC. and then TR. Please find. Okay, TR. And then if you look at the equation, you need information of beta and Q. Okay, beta, this one also from chapter 3. TR divided by TR. Also. So by using Reddit Kwong, alpha TR, okay, sigma, epsilon, what else? This one, please determine. Let's see. Please determine this one. Okay, once you determine, you have to use, if you look at here, 50 bar and 400 Kelvin. So what you have to do before you start calculation, please determine the phase. Okay, so this one is gas or liquid? I just want to know, gas or liquid? Gas. Okay, it's gas. So since you use gas, so please use that. Equal to 1 plus beta. U beta. Okay, and then Z plus epsilon beta. Z plus gamma beta. Okay, so start with Z equal to 1. Please calculate Z. I want to know. This one you learn already. Please calculate Z. Give me the answer. What is Z? Please calculate. You have to do the iteration, but starting Z not is equal to 1. Okay? Okay. So once you determine Z, okay, by using Radix-Wong, right? Okay, by using Radix-Wong, since Radix-Wong is epsilon, not similar with sigma, right? Okay, so you have to use case 1. Okay, this one I just erase. Okay, I just erase. You have to use this equation to determine I. Okay, you have to use this equation to determine I. Okay, so from that, okay, I equal to 1 divided by sigma minus epsilon. Okay, this one is 0. Right, this one is equal to 1. Right, ln Z plus sigma beta divided by Z plus sigma beta. So this one is 0. This one equal to 1. Right. Okay, just rearrange these equations. And then if you look at for the equation of residual properties for the HR, okay, residual of the enthalpy RT, right? Give me the answer for the Z. Z minus 1. Okay. D ln, okay, alpha TR. Right. Divided by D ln TR. Minus 1. QI. Okay. I, this one, you substitute. Okay. Q from the previous equation I show already. Okay. So the problem is this one. This one. Okay. So please take note. Problem is this one. Okay. How to determine this one? Okay. So since alpha TR equal to from the Radix-Wong, right? Alpha TR equal to what? Alpha TR equal to TR negative half. Right. So ln alpha TR equal to ln TR negative half equal to negative half ln TR. Okay? Because it's ln, right? So you can this one, right? You can bring it to the left side, to the left of the ln. So just do the derivation for this equation. Okay? So d ln alpha TR equal to d ln. You have to take note, okay, this one. I don't think there is in the textbook. Okay? So equal to half d ln TR divided by d ln TR. So this one you can cut, and then it's equal to half. Okay? So for the Radix-Wong, okay, for the Radix-Wong, if you look at here, this one, is equal to negative half. Okay? So the equation is become Z minus 1, right? plus negative half minus 1 Qi. Okay, this is only for Radicquang. For soft Radicquang and Peng Robinson is different. Okay, so please calculate delta HR RT. Similarly, also for this one is equal to negative half. Okay. Okay, just substitute. Later I will explain the equation, the derivation for the soft Radicquang and also Peng Robinson. Okay, Zach, I want Zach. Anyone? Kosong point 8026. Oh, Akmal Arif. Okay, anyone? 0.68. Anyone 0.86? 86 or 668? Okay, Li Chiao Yi. Okay, Fong Chi Yun. Okay, that one is the correct one. Okay, Arif, Arif, you can recalculate again. Please check your calculation. Okay, so you have to proceed to calculate the HR. I already give the what is it? The not value. I already solved for the derivation of the D ln alpha TR and D ln TR. Okay, please solve it. Can you calculate HR divided by RT? And then you can proceed for the residual entropy. Okay, residual entropy. Okay, today we just focus on the residual. Okay, not yet the I'm not sure we will focus on the hypothetical part or not later. But this one we just focus on the hypothetical part. But later not we just focus on the residual. But there is if the reaction is enter at 200 and then exit at 300, so you have to do hypothetical part and you have to calculate also delta Hij and also MDCPH also as well as MDCPS. You have to remember, but this one is just to focus on the residual. Okay, just be familiar first with the residual. Okay, how about the delta HR? I value of I first. I HR 0.1. Yes, that is correct. 0.323. Okay, 0.1 0.1323 and H lah. Kita HR. Oh, kawan. HR. Tiba RT. What is the answer? And then you have to calculate HR lah. HR, so you have to move here. Bring it to the right side. Okay. Give me HR. Anyone? How about HR? SR? HR, SR. Once you determine I, Q, beta, right? D ln alpha TR divided by D ln TR is equal to negative half. Just substitute into the HR divided by RT equation, so can get the answer lah, and just times with the RT. So you can get the HR value. So you can do similarly also for the SR. Okay. Give me the answer. Oh, Dr. Arlas mengatakan okay.
Sebenarnya benda ni kita buat.
4498226. Wait eh. 24. Okay lah. Okay, 4498. There's no yeah, negative. But my answer is negative 4505. Okay. That's the answer. Fong Chai Woon. Okay. HR, right? And that one is HR, okay? Already times with the R and T temperature. Negative 498.226 joule per mole. Joule per mole. Okay, thank you. And SR, I think you can calculate lah. Just substitute all the value. Okay. Can you do for the acetylene? Do for the acetylene similarly. Before we stop, please do for the acetylene. I want to know Z. Okay, and then I and HR. HR over RT. HR. HR lah. Just directly HR. And SR. Please do. I give you some time. Today we just focus on the cubic equation. Almost. Okay, give me the answer. Similarly, by using Frederick Kwong, okay? Okay, please calculate. I want Z, I, and HRSR. Okay. Z, anyone? I think this is the last tutorial before we stop. Okay. Just give me Z, I, and also HRSR. Previously, what is the value for SR for this example too? Give me the answer. Anyone calculate? Okay, just would like to remind you for the final, since final is face to face. So you have to buy main textbook, okay? If a copy or you print out from the what is it? From the ebooks, actually we not accept that one lah. Okay, if I think it's compulsory for you to buy the main textbook. So you can get from the link that I given to you, right? As well as I think it's from the Shopee also possible. It is a 8th edition, I think. The color is black and blue. Okay, so please remember, I think you have that books for the finals. Okay, I think that is one of the requirement for the face-to-face exam. Okay, because everything is there, the data, the equations. Okay, and I think you will use that book. If you want to buy from your senior also, is possible. I think for the another courses is like mass and energy balance. Last time also you have to buy. You're gonna use that book for for your plant design project also. Okay, and also process and project plan design books. Okay, that one process design later, plan design and plan design one and also process design, you're gonna use the similar books. That's why you have to buy also, because process design I will teach that courses, and plan design is like Dr. Zurina, Dr. Alapshiza, they will teach.
So
Yes.
about the SR,
Yeah.
the unit, is it joule per mole also?
Unit is actually is joule per mole Kelvin.
Joule per mole Kelvin. Okay.
Please check from the textbook. I think it's joule mole Kelvin. It's not similar with the enthalpy. Enthalpy is like a Q, right? Joule,
Yeah.
and then joule mole. Okay. Yeah. I hope that
And
you, yeah.
so the about the acetylene.
Yeah. Acetylene. Why?
It is using liquid Bruce.
I don't know. You have to check. Gas or liquid? I already teach you.
I think it's liquid.
Why? Why is liquid?
Depending on the TC and PC.
Okay, you have to check lah properly. Is it a liquid or gas? You have to justify. I cannot. I cannot justify.
It is certified through TC and PC, right?
Yes. You have to refer back at the chapter 3, right? And then you can use this PT diagram. You can justify just a sketch, right, from the PT diagram. If not, you refer to the table in the previous slide in chapter 3. This one. This is PT diagram. Please find the TC and PC. This one PC, right? This one is PC. Is it in this area or this area?
The lower.
Lower. This one. Sure. Are you sure? How about other student? This is vapor. This is liquid. Lower. This one. Lower is vapor.
Oh.
Lower vapor, right? Vapor or liquid?
Not sure.
This is vapor. Always got confusing. This is vapor. This is vapor. This is liquid. This is solid. You got in this area, right? This area, right?
Yes. So
This
it's
one is vapor. This is vapor. So it should be vapor lah. Use the vapor. Lower region. Acetylene, I think, is mostly even at the room temperature is gas. It's easily to evaporate. Last time when I did my experiment to detect the acetylene, if during winter I can detect that compound acetylene, but during summer I cannot detect this compound because it's evaporated during the summer. Okay. It's okay. So I have something to do actually. We stop here. Okay, please find the answer. Right. Solve Radicon and Point Robinson's. I will give the equation in the next class. For the D lone TR lah, D lone TR and alpha D lone TR tu kan. So that one. As well as if you look at here, there's already have a answer here down here. Okay, so you can refer here. So for tutorial 2 and 3, 3 I think is the later. Okay, I will explain in the next class. I will explain briefly about the it's a similar step, only the different at alpha D lon alpha TR divided by D lon TR, that one also. So I just give you the what is it? The derivations equations. Maybe in the WhatsApp group, or maybe in the class, during the class. But the procedure is similar, like by using a soft Radicon. Okay. Please solve it. This one I want to know the answer next week. Okay. And then we will move to in the next week we will move to the generalized correlations. We will discuss this one, and maybe we will do some short tutorial lah in the next weeks by using this Kessler, this one. Okay, please read first. So for the next week we will cover until here. Okay, because after that I think it's already the two-phase system. Okay, so two-phase system is the like the introduction before we move to the chapter 11. So we're gonna finish by next week actually. But just remember for this chapter, we mostly focus on the delta residual properties. Okay, but if you want to calculate the real thermodynamic properties, so you have to combine with the MDCPS, MDPH, or IDCPS, IDPH, together with the ideal gas, delta HIG or delta SIG lah. So you can get that actual thermodynamic properties. Okay, is it clear? Is it clear? Before we stop, any questions to use this cubic equation of state? So now we already covered the graph by using graph method, but not really recommended because it's going to take many steps. Okay, and another one is a cubic equation of state. Okay, but for the virials also we need information like a B, right? The parameters like a B. What else? What is the other parameters? This one. Okay, and also C, I think. Rho. Okay, this one is for the third truncated three-term virials. Okay, C, and also so this one is from the other references. So I don't really also not recommended for using this virials. Okay, if you want to use virials, you use generalized correlations virial equations. Okay, but later I will explain that one. So now we are focusing on the cubic equation of state. Okay, so I guess everybody can understands. Okay, and then I hope that you can finish this tutorial 2, and I will give the equation later for the soft Radicon and also Point Robinson. Okay, if you have no questions, that's all for today. Anything else?